The atmosphere are the gases around a planet. We're on page 141, by the way, 5.3. Notebooks for taking notes. Books
Is the
for
projector higher?
looking along.
He just said that.
Hey, now we're here.
Why? I don't like it.
So I can use the board underneath it?
When is lunch? Is lunch normal time? 12:50.
Yes.
Yes.
Next period.
Wait, 11:50?
We have the next period.
No. Wait, really?
Page 141. Page 141?
What's 140?
Yes.
I think everyone should just take a deep breath.
It's only 11:30, so if we don't eat till 12:50, yeah, we got.
I'm hungry though.
Well, what class are you in?
Period 1.
We're all overreacting.
Which means we don't know.
Okay, can we do this?
Having trouble with everything.
Are you on the right page now? 141?
Press now.
All right.
You okay?
Sorry. The atmosphere, the gases that are around a planet, and the Earth is mostly nitrogen. Most people don't know that. They think it's oxygen. No, most of this gas that's floating around right here is nitrogen. 78%. 21% is oxygen. And that oxygen is produced by living things. That's why it's there. 0.9% is argon, 0.03% is carbon dioxide. There's also water vapor. Anywhere between 0.1 to 3% of the air is water vapor. And depending on your area, you have more water vapor than others. Water is a gas that can hold a lot of heat. And so is carbon dioxide. So the atmosphere is very sensitive. As far as temperature goes, temperature is very sensitive to carbon dioxide and water levels. Since we are living right on the ocean, there's a whole lot of water in the air around here. So we have high humidity levels. And since water holds a lot of heat, our temperature, the temperature of our air doesn't change very drastically. It might be 85 degrees in the daytime here, and at nighttime it only goes down to 75. Because the water is holding a lot of the heat from the day. If you go out in the desert, though, it might be 100 degrees in the daytime, and it might get down to 30 at night. There's no water in the air to hold heat. Isn't that interesting? Like I said, oxygen is the product of living things. Before there were living things, there was no oxygen in the atmosphere. And oxygen very quickly binds to things. We call it oxidation. You put a piece of iron out and oxygen will stick to it, and then you got rust. You put a piece of paper on the wall, and oxygen will stick to it and change the color of the paper. You want me to prove that to you?
Whoa.
Huh? The oxygen hadn't stuck to that. That's what it originally looked like. Because the plastic is covering it up and the oxygen can't get to it. Isn't that interesting? That's oxidation. You ever take a bite of an apple and a few minutes later it's brown? That's oxygen sticking to the parts of the apple. So oxygen would quickly stick to things and disappear from our atmosphere if it wasn't constantly being replenished by living things. So if we ever find a planet out there in space somewhere, and we detect oxygen in its atmosphere, it's probably got life on it. Cool. We'll talk about the search for life later. So the atmosphere has different levels: the troposphere, the stratosphere, the mesosphere, the ionosphere. Anyone going to participate in Science Bowl this year? Waylon? You need to know this.
What?
The 4 layers of the atmosphere. The troposphere on the bottom
it going to be on the test?
The stratosphere, it could be. The mesosphere and the ionosphere. Now, all of our weather and everything happens down here in the troposphere. The first several miles of the atmosphere we call the troposphere. That's where the clouds are. It's where we live. You go above that, you have the stratosphere. And that's where the ozone layer is. Have you ever heard of the ozone layer? The ozone layer is a layer many miles wide of a molecule called O3, ozone. It's 3 oxygen molecules stuck to one another. And ozone has a cool property about it. It absorbs ultraviolet light. And so the ozone layer keeps ultraviolet light from the sun from getting down to the surface. Some of it still gets down, but not a lot of it. And so you'll still get a sunburn, but if the ozone layer was gone, your sunburn would be way worse.
Yeah.
You'd get burned up in just a few minutes. Be dead already from cancer, from sunburn. But luckily the ozone layer is there. From regular biology, you probably know, we started producing chemicals called chlorofluorocarbons, and we found out that they were eating up the ozone layer. And if we kept producing them, the ozone layer would disappear, and it would kill every living thing on the planet. So the governments got together, and they phased out that chemical and stopped producing it. This happened over the last 30 years or so. And eventually the ozone layer will recover, but we had already taken out a decent percentage of it. About 5% of the ozone layer was gone. What's that?
How long does it take to get like fix itself?
To recover? They estimate, hopefully, a couple hundred years. It'll fix itself. Because the sunlight will hit oxygen molecules, and some of them will come apart, and they'll come back together as O3. But that process takes a while. We managed to destroy a lot of it in about 50 years. And it'll come back in about 200 years. Hopefully. Well, for the next 200 years, we just have to live with it. Although it's not recovering as fast as they thought it would, and they're not sure why.
Maybe because there's a black market for that stuff.
There's a black market for CFCs. They've even included that in their calculations, and they still...
I was kidding.
Well, not a black market for it, but there are some countries that did not agree to the ban.
What?
Because their entire economy depended on those.
Yeah.
You could kill everyone in the country or keep making the CFCs. They chose to keep making the CFCs.
Well, making a CFC will kill everyone in the country.
And the scientists figure that's okay for a few places to keep making it. It's just the big producers like the United States had to quit. The mesosphere and ionosphere, and you can see this this line here shows the temperature. So the temperature is up near 300 Kelvin, that's Kelvin, at the troposphere, and then it goes down as you go higher up, and then it comes back up at the top of the stratosphere, and then it goes back down again. The ionosphere are ions, charged particles, that can, to some extent, get further up because their charges repel them from other like charges. And so the ionosphere is the furthest away. But none of these gases can really escape completely. They're pulled back to Earth by gravity. And you can see the pressure over here on the right. The pressure goes down and gets lower the higher up you go in the atmosphere. And this is why your ears pop when you go up in a plane, because the pressure is getting lower and lower. Even though they try to pressurize the cabin by pumping extra air in there, they can't quite keep up, and your ears will pop.
How high do planes fly on that?
Planes go, that's a good question. Planes go up about 30,000 feet, which is about 6 miles. Does it say how many miles high the troposphere is?
They go above the clouds. They fly.
Yeah, but I think those clouds are just showing you the highest clouds, how high the highest clouds get.
It looks like a little over 10.
The region below about 12 kilometers is the troposphere. So the troposphere is 12 kilometers. And 12 kilometers is about 7 miles. So even like a jet plane doesn't really go above the troposphere.
So it just goes above the lower clouds?
Yeah, when it shows these clouds here, there are clouds actually going all through here. So there are lower clouds down here. They're just not showing.
Planes go up 6 miles.
Yeah, about 30,000 feet.
Didn't know it was that high.
It's about 6 miles. Why would a plane go so high? Why not just fly low?
The air's thinner.
The air's thinner up there. You can go faster. The really fast planes go way up. But then they have to wear oxygen masks and stuff. It gets so thin up there, pressure suits. It's real cold up there. But you can go really fast when you get higher.
You know a planet is not shaped like a sphere?
What's that?
You know a planet is not shaped like a sphere?
A planet?
Yes.
Only if it's small. Once it gets big, it takes on a spherical shape because gravity's so strong it pulls everything to the middle, and so it becomes shaped like a circle, just like a water droplet is round. So once you get a certain size, you're shaped like a sphere.
How high can beyond like drones go that are like unmanned?
In the middle of pictures.
They can get a lot higher,
Like higher.
but I don't know how high. Eventually you get so, the atmosphere gets so thin it won't support a plane, and the plane sinks down to where the atmosphere is thicker. And I don't know how high that is, but I think it's like 8 or 10 miles up. So it's still here. We're getting real thin when we get up here. Okay, there's a process you need to know. It's called convection. And convection is the rising of hot air and the sinking of cool air. And it causes movement of the atmosphere. And also, movement of liquids will do this. Liquid convection. And this is what causes wind. And we're going to learn, we're going to see that there's wind on other planets. Especially the gas giants do a lot of convection because their gases are rising and flowing out and falling, like Jupiter and Saturn and Uranus. Has a lot of gases rising from it. More anus jokes.
It's like someone farted.
Right. Very good, Michael. Very good. So a hot road, the atmosphere will rise. I almost said asses. The atmosphere will rise, and then because it warms up and becomes less dense and thus lighter and will rise, and then it'll cool off and get more dense and fall back down. And so this is wind. You'll have wind blowing in from the sides of the road and coming up off the road. And so if it's windy out, that's because maybe air is rising where you are and blowing in from somewhere else. This creates all the winds on the planet. This convection effect.
Can you go back to the...
Convection causes the winds. That's how that can be summarized. Convection causes the wind. You know how fast the winds are blowing in the atmosphere of Saturn?
2 degrees Kelvin.
About 800 miles an hour. That's windy.
Faster than that.
I spoke a little bit already about the greenhouse effect. This is trapping heat in our atmosphere. There are 3 main molecules that do it. Water, methane, carbon dioxide. Those 3 molecules cause our air to be as warm as it is. If you took out all the water and all the CO2 and all the methane from the atmosphere, it'd be real cold. But luckily we have it. One of the things you've probably heard of is global warming. Humans produce a lot of carbon dioxide during our everyday activities. Burning fossil fuels. It puts extra carbon dioxide in the air and it makes the planet warmer. Not by much, because we don't produce that much. But it's enough to be noticeable. And temperature of the planet has gone up a couple degrees in the last 100 years. You might say, it's a couple degrees, who cares about that? I like it a little bit warmer. Well, the problem is that it happens to be going up in a logarithmic curve. And we're right about here on that logarithmic curve. And you can see it can get out of hand quickly. And so it's a little bit frightening of what might happen in the future if we let that continue to happen. If it doubles every 10 years, just like our population is doing. The human population is doing the same thing, by the way. And if it just keeps going up and up, you quickly run into problems. In my lifetime, the population's doubled since I was born. 40 years. It's about the doubling time. I'm 44. It's about the doubling time. So it's 7 billion now. It was 3.5 billion when I was born. So, gosh, if that happens in your lifetime, it's going to be 14 billion people by the time you get my age, or a little bit older than me. That's a problem. We already have enough pollution. There's already enough people, I think. So what are we going to do about it? Well, I don't know. I don't have a good answer. Not have as many kids. That's one way. And people are already starting to do that. Not have as many kids. Have to figure out some other way to get energy other than fossil fuels, because we're going to end up burning all those up. It's going to be water shortages. It's going to be food shortages. It's going to be lots of pollution. It's going to be hard to get away from it all. Probably need a lot of psychiatrists. All right. Sorry. Just kind of went off there.
Could you just filter, like, is there any way you can use the water from the ocean, filter that somehow, and then use that if we ran out of fresh water?
Oh, yeah. Yeah, there's plenty of water in the ocean.
Okay, so.
It's just expensive to do that. Yeah, they do that already in some places. It's expensive. So your water bill, instead of $50 a month, it's $300 a month. Well, some people can't afford that. It's like a lot of other things. And that's, you can clean up the pollution. You can even clean the extra carbon dioxide out of the air. It's just real expensive. So global warming, I already talked about that. That's humans releasing extra carbon dioxide into the air. And that'll be a problem you'll have to worry about forever. This is the temperature graph, showing how temperature has risen in the last 100 years. That's in Celsius. So, like I say, it's gone up about 1 degree Celsius, which is about 2 degrees Fahrenheit. And so his CO2 has gone up. And that graph of CO2 going up, that's the same as the population graph. The population graph has done the same thing. So CO2 has just increased with the population, which makes total sense because humans release CO2. So if you could level out the population graph, you'd probably level out the CO2. I think that's the solution.
Was that drop in the 1600s because of the plague?
No, this is CO2 abundance. Now, that one from the plague, they don't know why that was. They called it the Little Ice Age. They don't know why that happened. They think maybe it was because of something with the sun. Sunspot activity got real low or something, and the sun wasn't producing as much energy, and it got cold on the Earth for a while. And we don't really know why.
Because of the rent is cheap.
Ozone layer depletion, there's an extra reading section about it on 143. And that's the hole that's developed in the ozone layer. It's not really a hole, there's still ozone there, it's just less of it.
Like one of those giant droplets.
And it kind of sits over Antarctica. And it only comes up every spring. Every spring the hole opens up and then it goes back away.
Why?
It has to do with the chemicals and the way they're more active when it gets warmer. What's that?
Are like penguins dying because of that?
Thousands of penguins.
Um,
Skin cancer.
No, because there's not really very direct sun rays down there. If that hole were over the equator, there'd really be problems because the sun hits very directly. But here the sun is at such an angle that it doesn't cause that bad of a problem.
So the penguins are okay.
Penguins are doing pretty well,
Okay.
except that their entire continent is melted.
And that's negligible.
So far, yeah. Here's a little video showing the ozone hole. So, I guess the darker areas is less ozone. Or maybe it's the lighter areas. No, I guess it's the darker areas. So August, September. I guess maybe it's in the fall that we see it, not the spring. I said the spring. I may have been wrong on that. It might have been the fall. It's funny, just a few scientists can be credited for saving the Earth because they started measuring ozone concentrations and they saw they were going down. And then they figured out that these CFCs that we were producing were doing it. And those scientists got everybody to look at the data and we stopped using the CFCs. But if no one had ever been measuring it, we wouldn't have noticed. And the whole ozone layer would have eventually disappeared and people would have started dying. Not just people, but everything would have started dying from these ultraviolet rays. So in a sense, those scientists can be credited for saving everything on the planet. It's just a couple of guys.
Would it be a gradual thing?
Yeah, it would be gradual.
Like if people wouldn't just be like dropping out.
No, it'd take a few hundred years. You'd see more and more cancer rates. You'd see plants not growing as well. And they would have figured out why eventually if it weren't for those scientists. But it'd still be neat if you were one of those scientists. You could say, I saved everyone. Even though it's not completely true, but it's close enough. What about the moon? What about the moon's atmosphere? The moon doesn't have an atmosphere. It's too small. The moon not big enough to have enough gravity to hold an atmosphere. You see, it's an escape speed of 2.4 kilometers per second. And if you measure the speed of these gas molecules, they're moving faster than that. Gas molecules jump around, it depends on the gas, but maybe at 5 kilometers per second. That's how fast these air molecules are moving right now. 5 kilometers per second. But they're bumping into one another, so there's a lot of collisions going on. They say one molecule of oxygen makes about 3 billion collisions per second. Amazing how fast these things are going. And that's not fast enough, though, to escape the Earth's gravity. It is fast enough to escape the moon's gravity. So anything belched forth by the moon, any volcanic activity that was going on in the moon a long time ago, all the gases escaped. Every small body that we know of in the solar system is the same way. It doesn't hold an atmosphere. Now the next section, 5.4, talks about the interiors, the internal structures. And I talked about that yesterday. We know what the interior is like from earthquake studies. And here are a couple of different types of waves. Earthquakes have two types of waves, what we call P waves, which are pressure waves, and what we call S waves, which are sinusoidal waves. An S wave is what you do with a jump rope or any kind of rope when you kind of do like that and the wave goes through it. You know what I'm saying? This is an S wave. Yeah. I used to break dance a little bit. You know, it's kind of, just kind of some moves I have. I know it's impressive. There's a lot of great things that I do. And then a P wave is a pressure wave. If I push on the air, there's a wave of pressure that moves through the air and it reached you. Could you feel it? That's like Star Wars. And the thing falls.
When you're in a pool, like push the water.
Yeah, in a pool you can feel it. Yeah, absolutely. Yeah, because the water's so much thicker than the air. But it is really reaching you, and if I was pushing it fast enough, you wouldn't be able to feel it, but you'd be able to hear it. If I push it at 20 times a second, you'd hear it. It'd sound like...
There's a thing that you can get, and it's like a big thing, it has a little bungee and a plastic bag, and you pull it back and shoot it, it shoots air out of it.
That's cool.
Oh, yeah.
What was that?
And as it vibrates back and forth, does it make a noise?
I don't know.
It just-
It
it's
just
just
does it
like
one
a
time.
one-
You just pull it
yeah.
back and it does it one time.
Yeah.
You can hear it.
Nice.
Um,
Your ears are very sensitive to these pressure waves, and that's what sound is, pressure waves. Yes.
what's that? That's what it's called.
A sinusoidal. S-I-N-U-S oidal. O-I-D-A-L. And so these P waves and S waves move through the earth, you see? But they move at different rates. And they move through different things. Like P waves will go through liquid, but S waves will not. So here's an earthquake on the earth. The waves travel through the earth at a certain speed, and they can be detected everywhere else on the earth by seismic sensors. Little sensors they place on the earth can feel the vibrations of the earth. The earth is vibrating right now from small earthquakes going on in different places. It's not enough for you to feel, but it's enough for these sensitive equipment that geologists have to feel. And so the way the S waves travel is kind of in a curve, and the P waves too. So if there was an earthquake here, you could sense both P and S waves everywhere here. But right here, you can't sense any S waves. See, it says no S waves? That's because S waves won't move through liquid. We know this from experiments you can do in the lab here. S waves won't go through liquid. And so we know there's a liquid core right there, baby. Isn't that interesting? We know the size of the liquid core, and we know it's liquid. And we know from the density of the earth that it has to be metal. So it's liquid metal, like the Terminator. Read 5.3